Hey, Math 30-2. So today we are going to do relating the characteristics of exponential functions to its equations. So we kind of already did this with the previous one where we talked about, well, what's the equation? Here's the graph. How are they related? Okay. So when we write an exponential out, we usually write it in the form a, which is my coefficient, right? Times b, which is my base, to the power of x. And so sometimes the b is called the common ratio. Sometimes it's called the base of the function. It's what you're multiplying by each time when the x value goes up by one value. Okay? It's always going to be what you multiply by if you're going up in one root. So if it's like half, you always multiply by half. If it's 2, you multiply by 2. If it's 3, you multiply by 3. If it's 2/3, you multiply by 2/3. If you go backwards, you divide by those. You could divide by 2/3. You can divide by half or divide by 2. Okay? But if you're going forwards, what you're multiplying by. Okay? What we figured out from this, and some key things here, is that the a value, this a value that's in front, is always the y-intercept. It just happened to work out that way because, well, x to the power of 0, anything raised to the power of 0 is 1. Because remember what I was saying, you're multiplying a by b 0 times. So you're just left with a. That's all it is, right? Now b, the b here, that's your common ratio, okay? That's what you're multiplying by each time, okay? Now the graph is increasing, the key part. I'm not too concerned about a being positive, so that's what this is saying here. A is always positive, right? It's what happens when you change the b value. So if the b value is bigger than 1, then we have an increasing graph. So that would be example like we had before. So this could be up a 5 here, like 2 to the power of x. So this number here is greater than 1. Now if the b value, let's go orange here. If the b value is between 0 and 1, I'm sorry that these are two different lines here. If they're between 0 and 1, so an example of that would be like 5 to the power of a half, right? So that would be something between 0 and 1, right? Now be very careful that not all fractions are between 0 and 1. Like a fraction over here, like that could be greater than 1, could be like 3/2. Right, so that's greater than 1. So that would be an increasing graph because this number is greater than 1. As long as the denominator is larger than the top, so numerator, then you have a number less than 1, but greater than 0. So 2/3 would be okay. That would be a decreasing graph. So an increasing graph, I'm just going to do a little sketch here. It looks like that, so it's going upwards. A decreasing graph is the one that's going downwards, but not quite touching the x-axis. So those are those two types of graphs, increasing and decreasing. Okay, so what we already know about these kind of graphs is what do they have in common? We talked about this at the end of the last lesson. Well, they have one y-intercept. I don't know what this big blank is here. I know if this was x-intercepts, maybe I should change it to x. Maybe I typed this in wrong. Well, I'll put another dot down here. They have one y-intercept. Right, I'm just going to put down one y-intercept at a. So 0. Remember, dividing the y-intercept, you make x equal to 0. My bad. X equal to 0. A. Okay. So the a value is where my y-intercept is. Okay. They extend from quadrant 2 to quadrant 1. You can use Roman numerals there if you want. Right, I don't care. They have a domain of XER, and they all have a range of y has to be greater than 0. YER. Okay. And my last point here is that they have no x-intercepts. Cool. Okay, so it's nice before we go on to regressions and stuff and solving these, it's just nice to know if I see a set of data like I see here, how do I know it's exponential? Okay, So to know if it's exponential or not, is first of all, you have to look at the x values. Are the x values increasing at a constant rate? So you notice here it's plus 1, plus 1, plus 1, plus 1. Yeah, so everything's plus 1 there. They're all going to be plus 1. So here's plus 1, plus 1. They don't have to be plus 1. They could be like plus 2, plus 2, plus 2, plus 2, or plus 3, plus 3, plus 3. But it has to be increasing at a nice constant rate. It can't be jumping around. It's very hard to determine if it's exponential otherwise, if they're jumping around. If they are jumping around, we could just put them in a calculator, do a little regression, and see, does it match a regression, like exponential regression or not? Okay, now what you're going to do for the next numbers here, from the 6 to the 12 here, what happens? 6 to 12. Well, that's a times by 2. A times by 2. A times by 2. A times by 2. The last one, times by 2. So my common ratio, I should not use this pen. So my common ratio here is 2. Right? To figure that out, you just take a term. You could just look at some of these numbers. That's a times by 2, times by 2, times by 2. But you can always just take a term to find out what the common ratio is and take the term and divide it by the previous one. So 6 divided by 2, or 12, sorry. My bad. 12 divided by 6. 24 divided by 12. 48 divided by 24, et cetera, et cetera. They all end up being 2. So we have a nice common ratio by 2. So we're times by 2. Now this one, let's see. We're going to times by 2, looking promising. But then also we times by 4 here. That's not common ratio. So this one's not exponential. Okay, so that one's not exponential. And this one up here says if they are exponential, identify the y-intercept. So the y-intercept for this one was when x was equal to 0, so that's my y-intercept. State whether the function is increasing or decreasing. So the common ratio is 2, which is greater than 1. All right, so this is increasing. Plus also times by 2. The numbers are getting bigger as you go. Okay, what else? Provide my reasoning. Yeah, my reasoning is my little arrows there. Okay, so plus 1, plus 1, plus 1 on the top. On the bottom here, okay, my numbers are not going up, so I'm going to be thinking, okay, am I divided by something each time? Am I timesing by something? That's the key. What would I be timesing by to go lower? So what I'm going to do here, can't really just look at those. Maybe it kind of looks like it could be a 4 or something. I'm going to take the term and divide it by the previous term, and then kind of reduce that down. So I can pull my calculator here. Math, enter, enter. Okay, I get a quarter. Yeah, so that's, if I'm timesing by a quarter, it means I'm divided by 4. So I just want to double check. Now, if I take the 1024 and I times it by a quarter, I get 250. So that's what I typed in my calculator. All right, 1024 times a quarter. And then if I times it by a quarter again, I get 64. If I times it by a quarter again, which is just dividing by 2, I get, 4. I get 16. Divided by 4 again, I get 4. So they all have a nice common ratio where I'm timesing by a quarter each time. So my common ratio is 1/4. Okay, so it seems that it's common, so it's exponential for sure. My y-intercept is 0, 4,996 there. And is this increasing or decreasing? The numbers are getting smaller, so we're going to say it's decreasing. Okay. This number is less than 1, but still greater than 0. So that's very key. Okay. That's that. Okay, so let's think about, I'm going to split this lesson into 2 pieces as well. No, only 10 minutes right now, so I can do this next chart. But the reason I could do this next chart so quickly is because of all the things that all these exponential graphs and equations have in common, right? So these are exponential graphs. You can see the start in quadrant 2, end in quadrant 1. This one you can't really see what's happening at the end there. We can make an assumption that this is exponential. These are all exponential because the exponents have an x in them. And then you got some numbers in the front there. So the number of y-intercepts for all of these is none. So what I'm going to do, let me just zoom out here, or go all the way down here. Rather than writing none a bunch of times, it's none in all of those spots, okay? My y-intercept. Well, this one I'm just going to read off this. And my scale here goes to 5. There's 5 ticks. So this is going to be at a 2. So my y-intercept is 0, 2, or if you want to, just write down a 2. That's okay. This one here is 4. Okay, that's just reading off the graph. So that's easy enough. I can just read right off the graph and see what is across the y-axis. Pretty easy. Now, what we said before, the number that's in front of this exponent, that's not being raised to the power of the x. So like here, this number is being raised to the power of x. This number is in the front. So that is my y-intercept, 3.1 for the next one, and this one's 10 for that one. Okay, you can graph those and determine that. My domain for all of these, because I'm lazy, I'm just going to draw a big arrow down here. They're all the same. My range for all of these is going to be the same, always greater than 0. Okay. Now, these are going to be slightly different. Is it a growth or a decay? Is it increasing or decreasing? So growth is the same as increasing. Decay is the same as decreasing. So in this one here, going down, so the numbers are decreasing as they go from left to right. So this is a decay graph. That's what I just wrote there. Okay. So this is a decay graph, which is also decreasing, which is nice because they both start with a D. Right. This one here is a growth graph, which also means it's increasing. Okay. These ones, those ones, you're just looking at them. You're like, is it going up or is it going down? Okay. The next one here, you look at your B value, right? This common ratio, this is 5. 5 is greater than 1, right? So that means this is a growth function because it's going to be increasing, a graph function. Every time I do that little thing over there, it's just because the program, once I use my eraser, kind of really messes up. So I have to go right somewhere to kind of reset it. This one here, you can notice that this number is less than 1, but greater than 0, because the denominator is bigger than the numerator. So that means this is decay graph. Okay, then you go down. This is less than 1 because in the whole spot here is the 0. So this is definitely less than 1. So this is a decay graph. You can change 0.5 into a fraction. That's the same as saying like a half, which is less than 1, but greater than 0 because the denominator is bigger than the numerator. Cool. So those ones all slightly change a little bit, but they all have the same end behaviors from left to right, going from quadrants 2 down to quadrant 1, but stays in quadrant 1, doesn't quite get there. And the same thing, the other one starts in quadrant 2, but it looks like it's down in quadrant 3, but stays in quadrant 2. So they always go from 2 to 1. And there you go. Those are all the same. Cool. Okay, so these ones here, we can just do a little sketch. Okay. Now, for this sketch, I just want to indicate some key points on the graph, so I'm not too concerned about how accurate I'm going to draw these. I want to know, is it increasing? Is it decreasing? I just want to do it without using my calculator first. I want to think, can I think of this and just say, where's my y-intercept? Well, the number in the front is my y-intercept. So I'm going to put a 3 there. So I can go through all these and oh, there's a 4 in the front. Okay, so my y-intercept is 4. Remember, if you don't see a number in the front, you assume it to be 1. Here's 2.1. I don't know, right about there. So this is 1.9, so that's just less than 2. So I know where all of my y-intercepts are where they are pretty easily. Okay. Okay, now the next one, I'm going to think, what's the shape of the graph? Well, this number is greater than 1, so that's my b value is greater than 1, so that this means this is a growth function or increasing function. So it's going to be going upwards. Let's just put that here. It's going to go upwards like that. Now this number is less than 1. It's still greater than 0. So that means it's a decay graph. So it's going to be going this way. All right, so I can label these all off and say, okay, this one here is greater than 1. So this is a growth, a graph. Okay. And this one here is less than 1. So this is a decay. Awesome. So I know the shapes of these graphs. Now what I'm going to do is plot a few points. Let's see if that works. So I'm going to go 3 times 2, because 3 is my y-intercept. I guess that's my starting point, times the common ratio of 2.17. So my next point is going to be 6.5. 1-ish. And then I'm going to times that by 2 points. It's going to be way up my graph here, so it's going to be 14. So way up there. Okay, so I'm going to go 3 divided by, so I'm going to go backwards now. So I'm just going to go 3 divided by 2.17 to find the next point back. So I'm going to go here, so 1.4-ish, 1.3. And then I'm going to divide by 2.17 again and get 0.6. I'm just going to estimate it now, divided by 2.47. Okay, so the graph's going to look somewhat like this. So yeah, it's a growth function, just like we thought it was. And that skyrockets up there. Cool. Okay, so this one here is going to be 4 times 0.53. Okay, so that ends up being about 2.1-ish. My common ratio is 0.53 times by 0.53 again. So I get like 1.1 times by that again. I get 0.6. Like somewhere 0.3-ish. Okay, so it's going to go down. So yeah, decay graph like we thought it was too. So the graph's not the best there. Now remember, I go backwards. I'm going to be times, and I'm going to get like 8 something up there. I'm going to divide, sorry. That's actually just less than 8, isn't it? Oh, yeah, it's 7.5, sorry. Okay. Cool. So these ones here are pretty similar. I'm just going to pause the video and then pop back in with the graphs. Okay, I just want to show you something really quickly here. So I'm going to type that in my calculator because you have the same equation, 2.1 times 1.83 to the power of x. So I typed it exactly the way it is. So you can hit graph. I'm not too concerned about what the graph is. I know what it's going to look like. It's going to be a growth function. There it is right there. It's a growth function. All right, so it's going upwards. But what I want is some data points so I can plot them on my graph here. So I'm going to hit second graph instead and loads up a little table. And then I can use the data points here. So I got 0, 2.1. If I go up here, I can see some of my negative values as well. Right? If it wants to focus on that or not. I don't know if it wants to focus. Anyway, that's what you do. Second graph, we'll get to the table. You notice the x values are nice, but the y values may not be. But they're good enough for me to estimate where they should be here. So I'm just going to pause my video again. Okay, so here's my 2 graphs. You notice that this decay one, if you were to try to graph those points, like the first point back is like a negative, or is already at 27. It's way beyond my graph here. Because that number, this common ratio is so small, so close to 0. Now, if you were to think about that fraction, it means that you're dividing by a larger number, which means you're also, if you go backwards, you're going to times by a really large number. So it's pretty big. And there you go. The next lesson, we're going to be talking about how do we solve these. So say you have an equation, it's like equal to 5 or something. What would you do to solve them? We're going to solve it 2 different ways, algebraically and graphically. And I'm going to split those up into 2 different lessons there. And I'll see you in the next video.